Okay, let's check the volume again. Perfect. So we're going to do the equilibrium constant Kc for the reaction at a certain temperature as this one. If the concentrations, the initial concentrations are these ones, calculate the concentration of this species. So we got that the Kc is equal to 0.00431. Okay. The initial concentration of Br2 and by the way, I'm missing here the molarity, sorry, on both of them, the units. And it's important because which are they giving me? If they give you the mole, you divide it by the total liter. Here directly, you don't have to do it because they're giving you the molarity. So it's 0.0163 molar, and this would be molar too. So they're asking for the concentration of both of them in equilibrium. So the first thing, we're going to write our equation here. Okay, Br2 gas. Okay, and gives me 2Br gas. So the equilibrium expression for this, Kc, is equal to the concentration of Br to the square divided by the concentration of Br2. Now, we have something here that we don't know what direction is going. So when we do the ICE table, we don't know, we got the initials of both, but we don't know which, if you're going to form Br2 more or 2Br. How do we know that? Using the QC to know if those initial concentration would be if those initial concentration will make the reaction to produce more, for example, Br2 or Br. In other words, if you have very low this amount, the reaction will go to the left to produce more, so it can reach the equilibrium. If not, it will go to the right to reach the equilibrium. So for that, remember this. If QC, we don't know if it's in equilibrium or not, so we have to do the QC. That's why. QC, if it's higher than QC, it goes to the left, to KC. If QC is less than KC, it goes to the right. That's because if QC, the products are on the top. If we have too much product, like this one, it has to go the opposite way to use the product and balance the reaction to reach the equilibrium. So on the top, okay, we're going to have the initial concentration of Br, okay, to the square. So the concentration of Br is the same expression of the equilibrium. Hold on. To the square divided by the concentration of Br2. Okay, using those initial concentration, we're going to calculate Q and see where is it going, the equilibrium, the reaction. So Br is 0.0562 to the square divided by 0.0163. So the QC is equal to the QC. Let me erase this so that way you don't get confused. The QC will be equal to the concentration of Br divided by this, and it's 0.194. So what do we need now to compare it to the Kc of the reaction and of the disequilibrium? And the Kc value is 0.00431. 0.00431. So what is it telling you? That QC is greater than Kc, meaning that you have too much of Br to the product of Br compared to the equilibrium. Okay? So to reach the equilibrium, it has to go to the left. So 0. This is initial concentration, and this is the initial concentration of this. So the change would be to the left. That means that you're going to produce more Br2, more reactant, and this would be consumed. So the final concentration in equilibrium, 0.63, and here plus X, and here 0.0562 minus 2X. Now we use the Kc expression to find out the X, and it's going to be 0.0562 minus 2X divided by 0.0163 plus X. And to do it better directly, this is the Kc that is given. So here, let's substitute the value of Kc. Okay, and this Kc would be 0.00431. Now we have a problem here because we got a quadratic equation. Why? As this is 1, 2, 3. It's too small. So I'm not going to do the quadratic equation. You're not supposed to do it. But after finding X, the value of X is, this would be a quadratic equation. Let me show you. 0.0431. You cannot drop it because this is too big still. It has to be around -4. And then you have to prove that your assumption is correct. So you multiply this by 0. You took this to the top. Multiply both sides. Plus X equals 0.0562 minus 2X. So the X value, and by the way, to the square. This one I forgot to put to the square, sorry, because this is the concentration of products, and the products have a square, have a 2's coefficient. Okay, so in the equilibrium expression, Br, the product is to the square. So this would be to the square. Now, if you have this, it would give you a quadratic equation. If you solve, multiply this, multiply by this, and then you have the square of this. So I'm not going to do it. You probably don't have it on a test for sure. 0.0218. Okay, so knowing that this is x already, okay, you're going to go ahead and calculate the BR, which is this BR2 or BR, and it's 0.0562 minus twice x, and x is 0.0218. Do you see it? Because here the concentration of Br is 0.0562 minus 2x. Don't even think that you put it to the square, because the square is for the equilibrium expression. So what you need to do is solve for this, and it's going to be 0.0126 molar. And for Br2 would be 0.0163 plus x. 0.0163 plus x, and x is I'm gonna have to, okay, x would be 0.0218. So that gives you a concentration in equilibrium for Br2 of 0.0381 molar. So what do we do here? Here you get the results. My recommendation, and one of the things that is good to do if you have time, is substitute this equilibrium and see concentration and see if it gives you, right, the Kc, very close. And that would be a way to know that this is correct, those concentration. So the concentration in equilibrium of Br, and we're going to put on the top the Br2 to the square, right? Let me show you that one. Br to the square and Br2 on the bottom. Sorry if I said it the opposite way. So Br to the square, which is 0. Let me get the value. 0.0126 to the square divided by 0. This is not to the square. I'm substituting these values of concentration in equilibrium to see in the K expression, Kc, to see if we got it right. So doing this math, right, I'm going to pause it so we don't spend here we are. So if you look at this, right, you're going to have this, and it's going to give you 4167 by 10 to the negative 3. We put it in the 0.04167. and here is 0.00431, and I miss a 1 here, sorry, when I was showing how to calculate it. So it's very similar. I would say that it's the concentration is pretty accurate. Okay, volume. Let's continue with a few more problems, and this is the Le Chatelier principle, and we're going to study certain stress applied to the system and how affects the equilibrium and how the system will try to restore the equilibrium, because that's Le Chatelier principle. And it's basically when a stress is applied to a system in equilibrium, the equilibrium will counteract this stress to restore it. The system will counteract the stress, the external stress, to restore the equilibrium. Okay, so let's look at the increase in pressure and decrease in volume. According to the PV in ideal gas equation, okay, if pressure and volume are inversely proportional, and number of moles is directly proportional. So if you increase the pressure, okay, and of course decrease the volume, not enough as this, okay, increasing the pressure, okay, we don't take into account this, that it will move in the direction where is the least amount of moles. Okay, that means that if the delta N, which is the number of moles, the difference in number of moles of reactants minus, products. Delta N is always the products minus reactant. Of course, the N of the products minus the reactant. So if we increase the pressure, it will move to the least amount of moles. Amount of moles. So that means that if you have delta N negative, that means that you have products minus reactant, you have greater amount of moles in the reactant and reactants than products. And if if you have, this is an R, if you have greater amount of products, greater amount of reactant than products, okay, what is going to happen? The equilibrium will shift to the left. Okay, if you have a delta N positive, that means that you have more moles of products than reactants. So basically you do, okay, if the P increases, okay, it will, if it's negative, it will shift to the least amount of product, and which is, if it's negative, okay, will be the product. So it will shift to the right. In the case of more than the products, okay, have more amount of moles, that means that it shifts to the left. Why? Because if the pressure increases, right? The shift would be shift of equilibrium will go in the direction of fewer moles. Moles. Now let's look at this. Okay, at this one. Increasing pressure, okay, on the system, decrease, and by decreasing volume. How many moles do I have in the products? 2. Delta N here would be 2, and the reactant 3. So this is negative, meaning that the reactant have more moles than the products. So if you increase the pressure, right, the reactant here, the equilibrium will shift to the right because you have less amount of moles in the product than reactant. Okay, so it will shift to the right. Let me give you a little bit a table, and it's the if you increase pressure and decrease volume, if delta N is negative, okay, it moves to the right. Okay, if delta N is positive, it moves to the left. It shifts to the left. Now the opposite, if you decrease pressure by increasing volume, right? If delta N is negative, right? Positive, sorry, that means that you have more products than reactants, right? Well, it doesn't matter. We're going to do it the same way. So I keep that. Okay, we're going to do it the same way as the other one. If delta N is negative, what is going to happen? The opposite. Okay, the products will have least amount, but it will go to the left because it will go to the greatest amount of mole. And if delta N equals positive, it will go to the greater amount of mole. It will go to the right. If you have that in mind all the time, it's going to be easy to see this change. What would be the effect of adding O2 to the system? You're adding O2, and O2 is the reactant, so that means that to compensate, it will produce more 2O3. In other words, 3O2 would be consumed. So the equilibrium is moving to the right also. And then what would be the effect decreasing the temperature? Well, if this is an endo, what you have to think is then the K increase, the K, right, changes with temperature. But what you have to see here is that if it's endothermic, it's on the reactant side. And it's kind of like adding concentration to, you're increasing this, so the equilibrium, okay, if it's endothermic, okay, the equilibrium, let me write it down endo in a different way, okay, plus heat, you see, is endo in this direction, okay, 2O3 gas. So what is going to happen if you increase the heat, right? The reaction will shift to the right. But if you decrease heat, like in this case, you're decreasing the heat, right? By decreasing the temperature, the equilibrium will shift to the left. Okay, this is the answer. And finally, the other one is the catalyst is not changing. There's no chief because uh, it will change the speed of the forward and the reverse at the same time. So it's going to be no change in equilibrium. Let's not waste time on this.